Okay. Hello, everyone. Today, we are glad to have Junnan here. Junnan is currently a senior research manager at Salesforce Research. Before that, he obtained his PhD at the National University of Singapore. His main research focused in the building generative AI model that can understand and generate data in multiple modalities, including vision, language, and code. In particular, he is interested in the efficient multimodal pre-training. He believes in the value of open source research. So without further ado, let's welcome Junnan.
Thanks for the introduction. It's very happy to have this opportunity to share my work with you. So let me jump into the presentation. So at Salesforce Research, we are advancing vision and language AI from mainly two directions. In one direction, we try to build these libraries and tools for people to use, and we open source them. So one of the, I think, most popular one is this Navis library that we open source. It offers a one-stop solution for language and vision intelligence. It hosts some of the of our own pre-trained models, and including also source models. It supports a very easy to use inference and as well as model training, and you can also use it to download this data set and do benchmarking. So this is one direction on the library side. And also on the fundamental research side, we have been pursuing this for quite a while. We have a few papers that I will introduce briefly today, including this ALBEF, BLIP, and PnP-VQA, and also the recent BLIP 2. So in this talk, I'll mostly focus on BLIP 2. So then let me jump into the research part. So first, I want to talk a bit about what is this vision language pre-training and what we want to achieve by doing this. So the objective is we want to learn vision and language models that can understand input from both modalities and generate output. And these models need to be pre-trained to be easier to transfer to downstream vision and language tasks. And here, these tasks could include image captioning, image text retrieval, video question answering, and etc. So there are a few main challenges for vision and language pre-training. The most important one is this alignment problem, because images and text data, they are from very different domains, have very different distributions. And it's kind of hard to align their representations from these two different modalities in the same space. And the second challenge is more on the data side. So most works will use this internet data crawled from the web, consisting of image and text pairs. And those texts are mostly very noisy because it's not really human created, it's just automatic downloaded. And noisy in the terms that the text doesn't necessarily describe the content of the image, so it's not a really well-aligned image and text pair. So that's the second challenge. And the third challenge is more about the computation cost, because it's very expensive to scale up pre-training. So one of our biggest focus in our work is how do we design more efficient pre-training strategies. Okay, so then let me introduce a few works before BLIP 2. So the first work is ALBEF, Align Before Fuse. This was one of the first end-to-end multimodal vision and language encoder models published in year 2021. So our key observation is that in order to have a good multimodal encoder, we need to first do alignment. And this alignment is on top of the unimodal image and encoder and text encoder individually. So this ALBEF was at the same time as BLIP, and we utilize the same contrastive laws to perform this unimodal alignment. You can see that in the architecture, we have three main blocks. One is the image encoder, the second is the text encoder, and the third is this multimodal encoder. So we have three loss functions. The first is this image text contrastive loss applied on the image and text encoder to align their unimodal features. And we also have two loss that is applied on the multimodal encoder. So this is to learn more fine-grained interactions between image and text achieved via this cross-attention to the image. So these two laws are namely image text matching, which is a binary classification task that try to tell whether a pair is positive or negative. And also the third law is the mask language modeling, where you predict a certain missing word, you mask certain word from the text, and you try to predict it. Both of these will learn the more fine-grained image and text interaction. And in our paper, we find these three laws to be beneficial, mutually beneficial. And in the end, we can obtain a very good multimodal encoder to understand the both image and text input. And we also have some theoretical contribution where we unify these laws from a mutual information maximization perspective, which basically says that these laws are maximizing the mutual information between the image and text. So you'll see the similar three laws throughout all of our pre-training paper, and they have been proven to be quite useful in our models. Okay, so this is the first paper. The second is this BLIP paper I want to talk about. So this was one of the first unified model. So previously ALBEF was mostly an encoder model for understanding tasks. You can adapt it to generation, but needs to do some more fine-tuning. But BLIP is more naturally supported for both vision and language understanding tasks, as well as this vision to language generation task. So we did a slight modification to the architecture, where we still have similar three laws, but we modified the architecture a little bit so that it can support both encoder-based model as well as a decoder-based model. So you can see we still on the left have an image encoder, and we still have this contrastive loss between the image encoder and text encoder. But then we have additional cross-attention layers in the text encoder that can receive image information and do this image and text interaction within the model. And this encoder, this multimodal encoder can also be converted to a image to text decoder. And it is achieved by simply changing the bidirectional self-attention layer to a causal self-attention layer so that it becomes an autoregressive generative model. Otherwise, all the other parameters are shared. And so you have the same feed-forward network, have same cross-attention. It's only the self-attention layer are different between different functions of this model. And because we are training it to do image captioning task, which is a decoding task, we are using this language modeling loss instead of the master language modeling loss. So this design enables us to have a unified model. This is the model architecture side of BLIP. And there's another contribution from BLIP is where we found it's very important to improve the quality of the training data. I think this is kind of well known now with all the GPT stuff. People are doing instruction tuning. People realize that the quality of the data is probably even more important than the quantity. But in the visual language domain, I think we are one of the first to really propose some way to address this issue in a larger scale. So we have this very simple caption and filtering algorithm where we use a captioning model to generate synthetic captions. And then we use a filter model to remove the noisy captions. And because of our unified architecture, this caption and filter are naturally achieved by our own model. We can use this decoder to do captioning, and we can use this encoder, which can do image and text matching, right? So it can tell it's a negative or positive. We can use this model to do the filtering. So the way we do it is we first pre-train a model on the noisy data, and then we use the captioning and filtering to improve the quality of the data set. And then we retrain the model using the new data set. And we can observe a very good performance gain by doing this. And another observation we find is that when we generate this synthetic data, it's important to ensure the diversity of the caption. So we can either use nuclear sampling, the more stochastic approach, or we can use beam search. The beam search usually in benchmarks, it gives you a higher result, but we find if you use it as training data, it lacks diversity. It doesn't give you additional knowledge. That doesn't give you that much additional knowledge compared to a stochastic sampling approach. And we use the nuclear sampling in the end to bootstrap this data set. So this is a BLIP paper. And after this BLIP, there was a huge surge on these large language models, including this GPT-3 and the large T5 models as well. So we were wondering how we can exploit the power of these large language models for vision and language tasks. So this plug and play VQA was one of the first attempt we have. And the philosophy here is we want to utilize off-the-shelf models without any training. So that's why we call it a zero training approach. So we basically take existing models and we composite them together, and we make sure it can work together smoothly to achieve certain tasks. You may see some recent paper also are doing this similar idea, like also visual ChatGPT or some other papers are doing similar, but I think we are one of the first to explore this direction. So here you can see in the figure, we have 3 modules. We have a question answering module. This can be any language model that can do QA tasks. Because we are targeting for VQA tasks, that's why we are choosing a question answering module. And in our paper, we were using this fine-tuned T5 to do this. And also we have this image captioning module. The purpose of this module is to convert the image input into text input so that it can be naturally understood by the QA model. And if you just naively convert the image into captions, it is quite likely you don't get the good captions that is informative for your task. So that's why we have another module we call image question matching module. It gives us a gradcam interpretation, which is basically kind of heat map visualization to highlight the important regions corresponding to certain questions. And then we sample from this heat map, and we use the sampled patches to do this caption. You can immediately see the effect that the gradcam can highlight the areas corresponding to the questions. So here the question is about the black object. So it's being highlighted, and the captions will contain more information. In fact, it directly have this word olive in the caption appear very frequently. So if you ask the same question to the QA model, then the QA model will be less distracted by other information. It can give you the ground truth answer olive. And how do we achieve this image question matching? We just use the same BLIP encoder model. We use the image text matching, and we just treat the question as a native text, and we visualize the gradcam. So we were able to achieve quite good performance on zero-shot VQA by doing this, but there's still a few limitations. First of all, the QA model, you need to convert into captions, and this creates a lot of redundancy in either the compute or the amount of information you are given to the QA model. So usually we need to generate 50 or 100 captions, and this makes inference quite slow, in particular if you have a very large language model. And secondly, is mostly still for QA tasks. So if you want to extend to other tasks, you need to do some more designs to, or need to do some kind of training. So it's no longer will be a zero training framework. And then we wonder, can we directly have a model that can, given images, can convert this image to something that is understandable by the language model? So we do some soft prompt to the language model instead of giving it captions. So this motivates us to do this BLIP tool, which we believe is the correct way to utilize large language models to this vision and language task. And we believe this will drive the new innovations in this domain. So in BLIP 2, we have a few key contributions. The most important one is we were able to make any frozen language model to understand images. And this is very efficient process. And we also was able to leverage not only pre-trained language model, but we also use pre-trained image encoder, because there are a lot of good works in doing this pre-training of vision transformers. And it feels like a waste if we don't utilize those, because they already give us very good visual representations that we can directly utilize. And then the challenge becomes, how do you align these two models? So you have a frozen model, you have a frozen pre-trained VIT, and there's a big domain gap because those two are trained in more like a unimodal fashion. They don't share any information. So then the key technical challenge becomes, how do you bridge the modality gap? And we were able to do that, which I'll introduce later, how we achieve that. But after we achieve that, we find some interesting behavior begin to emerge. In particular, if you use a language model that can follow instructions, then it can follow multimodal instruction. So you can give an image, you give an instruction, and because this language model was frozen, and now it understands the image, it can understand the instructions about this image in a zero-shot way. So this enables what we call zero-shot instruction following image to text generation. And lastly, our training approach is very efficient, mostly due to two reasons. One is we were using frozen models, so most of the model parameters are not trained. And secondly, even for the trainable part of our model size is very small. So we only use less than 200 million parameters as trainable ones. Compared to other works, this is almost negligible cost. Right. So then let me talk about how we achieve this. How do we bridge the gap? So we introduced this architecture. We call it a querying transformer, and short for Q-former. And this architecture, the purpose of this model is to be able to extract visual information that is most aligned with the text. So in some way, it is converting the image encoder's output in the text space. So how do we do that? We need to do it with a stage pre-training. In the first stage pre-training, we plug this Q-former to the image encoder, and we do vision and language representation learning to align the representation from the Q-former more to the text space. And in the second stage, we plug in this additional language model, and we just do the naive generative loss. So given the image, we generate the text. And this second stage is proven to be quite efficient. You don't need too many data or too long training to achieve good second stage, given that you must do the first stage. So this first stage is more important and more expensive, and it learns a very good representation so that you can easily align it with a language model. So then let me dive deeper into these two stages. So in the first stage, we were training this Q-former. So what is this Q-former? You can consider this just a transformer architecture. Actually, we were initializing this model from weights from BERT. So this is just a transformer. But there's this additional queries. So if you are familiar with detection paper, you may see this in the DETR kind of work, where you have a set of learnable queries. Those are just vectors. You can consider them to be part of the parameters of the model. And each query will be given to the self-attention layer, and it will interact with each other, and also it will interact with the image. So the query's main purpose is to extract features from the image. So pass through all the layers, all the blocks of this transformer. And in the end, each query will produce a feature. And this feature will have a lot of information about the image. So now we want this query to be able to extract features that is most relevant to the text. So we achieve this by also giving the text input to the same transformer. So they share the same self-attention layer, but the feed-forward layer, we decouple those to be kind of two set of parameters. And we train this with the same three laws you have seen before in BLIP, namely the contrast laws, the captioning laws, and the matching laws. But we need to make some tweak because now we are not using a trainable VIT. Instead, we are using this frozen VIT and we have these queries. So the first tweak we make is that the contrast loss is not applied to the image encoder, but it's applied to the output from the queries. So we have this queries with the output images features, and we have the same the transformer, it output the text feature, and we contrast you alignment between these two set of features. And during this, there's no interaction between the image and text. So you can see that we have a unimodal attention mask where the interaction between those two modalities have been blocked due to this contrastive loss. And second, we have this image text matching loss, where we just enable the bidirectional attention. So right now, the query and text, they can see each other. And in the end, the queries will produce some features, and this feature will have information for both image and text. And we try to see if it's a match or if it's a positive or negative pair. And thirdly, we have this captioning loss, where we first input the queries to the model. So the queries now have a causal attention mask with respect to the text, meaning that the queries can see each other, but they cannot see the text. The text can see the queries, but the text cannot see the image feature directly because it doesn't have any cross attention. So the only way the text can know about the image is through the queries. So by doing this, we were enforcing the queries to learn the most important features from the image that can be used to generate the text. So you can see actually all these three losses are serving the same purpose. Is what we are aiming for is to learn query features that can extract the most text relevant information from the image. And this means that this condensed information is very high level semantic meaning of the image that can be directly used in our second stage to be given as input to the language model. Okay, so next I'll talk about the second stage. So this second stage is relatively easier. We have a frozen language model, and we have this Q-former, and the Q-former will produce some output features based on the queries. And we just project these queries to the same dimension as the language model's input embedding. Okay? So we have a FC layer to do this. And this will be just kind of soft prompt to the language model. So you give these initial embeddings to the input layer, and you ask the language model to generate the text. And then you train only the Q-former, only the yellow part. We are frozen the language model because we find that if you fine-tune the language model, it may hurt the zero-shot performance due to some catastrophic forgetting behavior. And one of the main reasons is that we are training on this caption data, which doesn't have a very complex text. So the text here is doesn't contain as much knowledge as what the language model has seen before. So that's why we need to keep it frozen. Yeah. And here, not only we try the decoder-based language model, we also try the encoder-decoder language model. We use a PnP-5. And because there's additional encoder, right, we need to split the text into two sections. We give the prefix section to the encoder together with this visual features, and we ask the decoder to generate the rest. So this is basically how we train the second stage models. And then after we train this with just naive image and text, pair image caption data, we found out that the model can retain its capabilities to follow instructions. So here we use the PnP-5 model. Then we so previously you have this prefix text, right? So in the training, it's just a subset of the caption, but during inference, we can give it an instruction instead. We pass this instruction as input, right? And then we ask the decoder to generate the output. And you can see that it can understand things that it doesn't really see during training. We don't have QA data during training, but somehow because of this language model's capability to generalize to different instructions, it can understand questions and answer questions. It's very, you can see some questions requires quite complex visual reasoning capability. You need to understand also the shape and also the slide to answer this question. But we find surprisingly the model can answer these questions. And one of the key reasons we believe is we already have very good alignment. So the visual and language alignment is done in a very good way so that the language model can understand the visual information quite well. And of course, there are some limitations. For example, this is still unsupervised training. So because of most limitation from the PnP-5 model, it's not perfect in understanding a lot of other instructions. And you may see there are some recent works, this mini GPT-4 or this Lava paper from Microsoft. They were using this Vicuna model, fine-tuned from Llama. So that's a instruction-tuned decoder model, which provides more conversation like output, better than PnP-5 in the conversation aspect. Okay. And you can do tuning with that model, will give you better conversation capability. Right, and just to show some numbers here, so we were able to achieve very good performance compared to existing models. So on VQA and GQA, which is more about the visual understanding part, we can outperform even the 80 billion Flamingo. We were lagging a little bit behind on the OKVQA because this data set is more requires more on the knowledge part, which is mostly from the language model. So that's why their 80 billion model have better knowledge compared to our 11 billion PnP-5 model. And you can also compare the trainable parameters. You can see that we are very, very efficient in this aspect. And if you train a Flamingo, you cannot train with 8 or 16 GPUs very easily, but we can do that without much problem. And I believe we can finish the training with 16800. You can finish the training for the second stage within 1 day. So that's you have a new Vicuna model, you fine tune the Q-former, you can do it within 1 day to obtain reasonable result. And we also have some result for fine tuning. So we can actually fine tune the model. In particular, we fine tune the VIT part. So we still keep the language model frozen during fine tuning. And we are able to achieve quite good results on this captioning task. You can see on this no caps zero shot, we can achieve SOTA performance. And much better than BLIP1 actually. And BLIP1 have more trainable parameters. So this really shows the power of these language models in generating text. And we can also actually use BLIP2 for retrieval tasks. So for retrieval, we actually don't need a language model. So we just take the first stage pre-trained model that have very good visual and language alignment. We have this contrastive learning, we have this image text matching, which can be directly applied as a retrieval model. And so we can fine tune it a little bit on Coco as well. And we can actually get SOTA for the retrieval benchmark better than this base3 model, which was have a lot more trainable parameters. And just to show one important ablation study to show that it is crucial to do the first stage reputation learning to align the vision and the text information. So if we throw away the first stage, if we just do the second stage, generative learning, we just train the model to generate text. So we have the LLM and the image encoder and two format together. We train end-to-end to generate the text based on the image. Then the performance becomes very bad. This is something have been done by previous works. I believe Flamingo is doing something similar. They are directly training the generative loss, so they don't have this Q-former loss, and they do observe some catastrophic forgetting problem, and they need to do some tricks to alleviate that problem. And we achieve a similar thing. So if we don't do any tricks, we just directly fine-tune it with a data set. You can see the OPT model is very bad, meaning that it's not aligned to the visual information at all. As you train for longer, the VQA performance even become worse. So the captioning performance will become better, but still much worse than our second stage, two-stage model. But as the captioning improves, the VQA becomes worse, meaning that it is not really generalizing. It's just overfitting, and there will be forgetting problem if you overfit too much. And similar for PnP-5, it's better. It's not really forgetting, but still, because of the poor alignment, the performance is much worse, 20% worse than our two-stage training. So I'll finish with some examples some are from us, some are from the community, to showcase what this BLIP tool framework can achieve. Right, these are of course cherry-picked ones, so you don't expect to be always this good. In particular, we are only doing unsupervised learning. So you can see it can kind of serve as a product intelligence agent. You can answer questions about this product image. It knows the suitable age. It knows what this product can do, and also it can recommend some similar product. And it's not also kind of a knowledge-based assistant. Right? You can ask it about knowledge about the picture that you don't really know before, and it can answer with quite decent accuracy. And it's here, this example is correct. It's noise from the emperor of the Qin dynasty, and the purpose is to provide protect meters. And I also tried this example where I use SD stable diffusion generated images as input, and it kind of reconstruct the original prompt quite reasonably well. So this was the prompt to generate the image. And if I do a captioning, it's also a Pikachu sitting at a table in front of Eiffel Tower. So this is kind of interesting behavior, and I believe there may be some research opportunities if you combine BLIP tool and stable diffusion in some way to improve your model in a circular fashion. So lastly, I want to share some failure cases as well. So like I said, this PnP-5 have some limitations, and also our vision language training have some limitation as well. Mostly, I believe, is because of the data quality. So if you can improve the quality of data, maybe you get better results. So here it can have inaccurate knowledge. So it's saying a wrong code from Einstein. It can have a wrong reading. So it's not really reasoning about whether this shirt is suitable for the weather. And also the knowledge is not up to date because we are using older data set. It doesn't know about iPhone 14. So its answer is iPhone 11 instead. But this, I believe most of this problem can be fixed by higher quality data. Okay, I think that's all that I want to talk about today. Yeah.